So in the previous class, we saw that the most important thing was to figure out the limit of the sequence. So here is the most important result in this section, and that is the theorem which says limits of a sequence can be found from limits of a function. So suppose f is a function such that f of n is a of n for all positive integers n, then if the limit of this function f of x as x goes to infinity is L, then the limit of the sequence is also L. So what it basically said is the following. So suppose you have a sequence an. Let's take the simple sequence 1 over n. Now the function that generates this sequence would be f of x, and all that you have to do is replace the n with x. So that is 1 over x. Now when you write something as a function f of x, then x is real numbers. So now x are real numbers, and therefore we can study this and find limit using techniques that we learned in Calc 1. So if you remember in Calculus 1, we figured how to find limits of functions. So whatever is the limit of this function, the same would be the limit of this sequence. And the reason is actually quite intuitively obvious. If you were to graph the function f, then your graph of 1 over x would be something like this. So f of x is 1 over x. Now if you think about the sequence, all that you are doing is picking points on this graph at discrete intervals. So all these terms of this particular sequence would be sitting on this curve. So wherever the function goes, so goes the sequence. And that's the idea. And it's a pretty neat idea because we know so much about finding limits for functions. So let's look at an example and then we'll come back to practicing more. So here our sequence an is n over n plus 1. So step 1 is figure out the function f of x, which is trivial. All that you have to do is write x wherever you see n. Now step 2 would be find the limit of x going to infinity of the function x over x plus 1. So what is this limit? Now one approach is algebraic, the kind of stuff that you did in Calc 1, and the other one which we learned recently is the L'Hopital's rule. So I'll remind you again when we have to use L'Hopital's rule. In this particular question you really don't have to, but sometimes you have to use the L'Hopital's rule. So let's find this limit. So if you remember, the trick used to be that you would divide the numerator and the denominator appropriately. So I can divide the numerator by x and I can divide the denominator also by x. So if I do that, I get 1 over 1 plus 1 over x. Now as x goes to infinity, the numerator stays 1 and in the denominator you get 1 plus, now this term goes to 0 as x goes to infinity. So you get 1 over 1 plus 0, and that is obviously 1. So that is what this is saying, that the limit of the function is 1, and therefore the limit of the sequence is also 1. And you can see this graphically, that this is approaching this line 1. Now before we practice more, let's just go through few results and some terminology. So here are the limit laws of sequences, which are intuitively pretty clear. Suppose you have two sequences, one is an, the other one is bn. An converges to a, bn has the limit b. Then if you were to add or subtract an, bn, an plus minus bn, the limit would simply be a plus or minus b. Makes sense? Now limit n going to infinity c times a of n. So if you just multiply a sequence with a number c, all that is going to happen is that the limit would be c times a. In other words, for example, suppose I had a sequence 5 times 1 over n. So what would be this guy's limit? It would be 5 times 1. So that would be 5, because 1 over n has the limit 1. Similarly, if the two sequences are multiplied, an times bn, then the limit would be a times b. If they are divided, the limit would be a divided by b. Okay, some terminology. Now, none of these things are really needed in this particular course, but it's nice to know these terms. So we say a sequence is increasing if an plus 1 is greater than an. Makes sense? If the next term is strictly greater than the previous term, then it's an increasing sequence. So for example, 0, 1, 2, 3, this is a increasing sequence. Now an is non-decreasing if an plus 1 is greater than equal to an. That means it may not strictly increase, but it definitely does not decrease. So example is for 1, 1, 2, 2, 3, 3. So it is not going down, but it doesn't increase strictly. Similarly, we have for decreasing and non-increasing. Now the new phrase here is monotonic. So an is monotonic if it is either non-increasing or non-decreasing. That means basically it moves in one direction. So if a sequence does behave in this manner, it's called monotonic. The next one says an is bounded above if there is a number m such that an is always less than equal to m. Then it's called bounded above. So what that means is that here's your sequence which is going along like this, but there is some number m and it always stays below this, never crosses this. Then it's called bounded above. Now similarly, if you have a sequence that goes around and does things like that, but never goes below this number n, so we call this is bounded below. So here you have bounded below. This was bounded above. Finally, a sequence is called bounded above and bounded below, then we call it a bounded sequence. So if a sequence stays between two numbers m and n, so it always stays here, something like this, then it's called a bounded sequence. Here is another example of a sequence which converges to 1, and you can clearly see by its direction in the graph that it converges to 1. Another kind of sequences that are of interest are geometric sequences. So these are, you will see the definition in a minute, geometric sequence. So that means here you have an to be 0.75 raised to the power n. So as n goes from 1 to infinity, you get the terms for it, and if you graph it, you will notice that it goes down to 0. So if r is between 0 and 1, the sequence will converge to 0 and is monotonic. It will go down to 0 and it will be monotonic. That means it will have one direction only. That means keeps reducing. On the other hand, if we have this one, it's negative 0.75 raised to the power n. Now from the graph you can see that it does converge to 0. However, it's not monotonic. It's not monotonic. It oscillates. So first you would be here, then you would go up, then down, then up, then down. But however, still you would converge to 0. Another example, here r is greater than 1, and when that happens, the sequence obviously diverges, because as n increases, an increases to infinity. And finally, if you have a negative sign in r, then not only does it diverge, it also oscillates. So all this is put together in this particular slide. So you can read it and see how it's put down compactly here, all the examples that we just saw. Okay, in the next class, we are going to practice problems of finding limits. So let me quickly review that the prime objective this section are the following. First thing is to understand the behavior of a sequence and how it is distinct from the idea of infinite series. We'll come to infinite series very soon. And then we have to understand and be able to find the limit of a sequence, obviously if it converges. If it does not, then it diverges. And to find the limit, the most useful theorem is this limits of function approach. So we'll continue with these examples in the next class.